All right, so our goal today is to talk about dynamics. Now, dynamics problems are those in which we have an acceleration. So this is not dynamic equilibrium where you're moving at a constant velocity. We're going to look specifically at dynamics where we are not in equilibrium. So with all of these problems, we are going to have a non-zero net force. And if we have a non-zero net force, then our net force is equal to mass times acceleration. But technically our acceleration is a vector. And if I'm not careful, I could end up with a net force in the x direction and a net force, well, that would be the y direction, and a net force in the x direction. And with that, I would therefore have a acceleration in the x direction and an acceleration in the y direction. And I do not want to have that. So our goal with when we set up our free body diagrams, when we rotate our axes, our goal is to have our acceleration in only one dimension. So it is either an acceleration in the x direction is equal to a, and our acceleration in the y direction is 0, or our acceleration in the x direction is 0, and our acceleration in the y direction is equal to a. That is our goal, is to meet one of these two situations. And that's so that we don't have to do vector acceleration on our ax and ay and then find a net acceleration from that. I don't want to have to combine those together and get a separate magnitude. I want to set it up to them in that way. So that's part of the reason why we do the process that we go through. So we're going to look at an example. Oh, actually, before we do an example, what are the steps that we should take when we're solving these problems? What are our problem solving steps? Well, the first thing you're going to do is, of course, read the question carefully. Make sure to underline or circle very important key points. So things like frictionless, constant velocity, with friction, anything that would allow you to determine some special circumstances. Starts at rest, ends at rest, anything along those lines. The next thing you do is you draw your free body diagram, following all of our free body diagram rules. You will then write your net force equations, write your Fx and Fy. Even if it's a one-dimensional motion and say you're moving only in the x direction, you should still write your Fy directions with your free body diagrams, because sometimes if our net force in the y direction is 0, there might be a point on the AP exam for acknowledging that it's 0 and that your net force is only in the x direction. So don't skip those steps. Do both. And then what you're going to need to do is you're going to need to sub in equations, non-variable equations, if possible, into your net force equations. So that would be doing things like subbing in Fg is equal to mg, or our friction force is equal to mu Fn, things like that. Sub those in non-numerically. And then you will algebraically solve for the unknown. So whatever it is that you're looking for, it may involve a systems of equations, and you do this non-numerically every single time. And then your very last step, that is when you sub in numbers. You will box your final answer. You will check to make sure that that final answer has units, appropriate sig figs, 2 to 4, just do 3, and then that it also has a vector direction if necessary. So if it's asking for the net force, that's a vector. If it's asking for the magnitude of the net force, that is a scalar. So you have to make sure that you check that with your answers. Now the only exception I make is when you have to sub in numbers, is you can always sub in, at this step right here, you can also sub in zeros. If something is 0, you can sub it in at that point. Okay, so we have a situation. This is a very typical problem. Sometimes these will be accompanied by pictures, sometimes not. So you have to get used to reading and drawing your own diagram from the question setup. So we have a block of wood being dragged across a table by a rope at an angle of 50 degrees above the horizontal. We have a coefficient of kinetic friction between the block and the table is 0.40. The mass of the block is 5 kilograms, and we have a known tension in the rope, and our goal is to find the magnitude of the acceleration of the block. So because it's asking for a magnitude, that means we do not have to worry about a vector direction at the end. So our goal is to find the acceleration. So that's what we're looking for. It's giving us some clues. It's giving us some clues that, well, there is tension, there is kinetic friction, and we know quite a bit about the tension and the kinetic friction, which is nice. It doesn't mention anything else. It does mention mass, which implies that, of course, there's a gravitational force, which implies, of course, that there is a normal force because we are sitting on a surface. So the first thing I would do is, because this one doesn't have a picture, is I'm going to draw a picture for me. And I'm just going to assume that it's being pulled to the right. And so I've got a rope of 50 degrees. So I'm going to label that as theta equals 50 degrees. I would add on, for example, that I know my tension. Let's see. So I know that I have a tension force that is equal to 20 newtons. I know my coefficient of kinetic friction is 0.40, and I know my mass is 5.0 kilograms. So that is, for me, that's all part of reading the problem. Okay, I've read the problem and I figured out what I know and what I don't know. So if I wanted to solve this problem, the next step after I've read the problem and kind of had a good feeling for what's going on is I'm going to draw a free body diagram. So I'm going to come do that over here. So here's my box. So I know I'm going to have a gravitational force. And we've worked through the setup of this problem several times, so I'm not going to go in super extreme detail. I know that I'm going to have some sort of tension force. And my tension force is 20 newtons. My force of gravity is going to be 5 kilograms times approximately 10 meters per second squared for the acceleration of gravity. So my weight is about 50 newtons. So I'm going to make sure that my tension isn't super huge, just to kind of get a relationship between what's going on here. So we have a force of tension, maybe a little smaller. Going there, we have an angle of 50 degrees. And then I am going to have friction force. It's a kinetic friction force. And I'm going to have an acceleration. So I know that my friction force is present, but it needs to be smaller than my horizontal component of tension, because I do have an acceleration in the direction of motion. So I'm going to label my friction force. And then I'm going to draw my normal force so that it is larger than my friction force, because I know it has to be, and so that it adds up with tension. So let's see, it needs to be something like that. So that looks approximately right. So, and I might shrink my kinetic friction force just down a little bit more to make sure it's really obviously smaller than my normal force. So this problem does come with a lot of numbers, which is really nice. So you could actually solve this one pretty easily, but we're gonna go through the whole process. So I have my free body diagram. Now, because I'm gonna eventually wanna write net force equations in the X and Y direction, my tension being at an angle is a problem. So I am going to draw in my axes. I'm going to identify my positive x-axis to be the direction of the acceleration, and my positive y-axis to be up. And then basically I'm going to resolve this tension force into an Fty and an Ftx. And I'm just going to label that angle theta here, so I already know it's 50 degrees over here. And then I'm going to put that squiggle through my tension because I'm not actually including it in my diagram anymore. And of course, everything I just did here with adding the axes on, you do not do that on the official AP diagrams. So my next step is to write net force equations. When you're working these problems out on an AP free response question, part A is usually to draw the diagram. Part B is to solve for something in the problem. Do not, just as a habit, write your net force equations up next to your diagram if you're working a free response question. Make sure you write your net force equations where it's relevant in the problem, because the graders are not going to go back and hunt to see, did you write your net force equations down somewhere? So when you're working at a problem, like a step-by-step free response question, make sure you put your work where it's relevant. But in this case, I don't have any parts to this, so I'm just going to write it up next to it. So I'm going to have a net force in the x direction, and I'm going to have a net force in the y direction. And I always do this entirely non-numerically, and I start with the simplest way that I can write it, with it using as few terms as possible, because this is a conceptual representation of my understanding of the situation. So I don't want to go subbing in a whole bunch of stuff, because if I make an incorrect substitution, I don't have a basic representation of understanding. So my net force in the x direction is going to be my Ftx minus my friction force, and that's going to equal m times a, because that is the direction where my acceleration is. There is no acceleration in the y direction because this box is only moving horizontally. Now in the y direction, I'm going to have my Fn plus my Fty minus Fg, and that is equal to 0. So I've now set up a conceptual understanding for what I'm looking for. Now I'm looking for acceleration, and so I'm going to start with that equation. And see, I don't always need both equations to solve a problem. So let's see, can I just do it with the x equation? So I'm going to take Ftx, and Ftx is the adjacent side, so that is going to be Ft cosine theta. So I'm substituting in equations for things that I know, non-numerically. My friction force, I don't know it, but I do know the coefficient of friction, so I'm going to sub in UKFN for my friction force, and that's going to equal m times a. So if I was looking for acceleration, do I have everything I know to use this equation? Well, I know my tension force, I know my angle theta, I know my coefficient. I don't know my normal force. I do know my mass. So I have two unknowns, so I need two equations. So I'm going to have to go over here and use this equation to find normal force. Well, I can solve for normal force, and I get normal force is going to equal Fg minus Fty, just solving this equation for normal force. And then I can sub in non-numerically. My normal force is going to be mg minus Ft, and the y component is the opposite side, so that's sine of theta. I can then, when I'm showing my work, I'm going to show that I'm going to take this quantity here and I'm going to sub it in for normal force. So I'm going to go through and take Ft cosine theta, leave that as it is, minus mu k, sub in mg minus Ft sine theta for Fn, and then that is going to equal m times a. So if I were to solve for my acceleration, I would get that my acceleration is equal to Ft cosine theta minus mu k times mg minus Ft sine theta all over mass. All right, so we have our equation for acceleration non-numerically. We now need to sub in our answers, our numeric values to get an answer. So I'm going to take that up here to the top so I have more room. So my acceleration is going to equal my tension times cosine theta. So that's 20 newtons times cosine of 50 degrees minus my coefficient, which doesn't have units because it's dimensionless, times my mass, 5.0 kilograms, times 9.8 meters per second squared, minus my tension force is 20 newtons, this time times sine theta, sine of 50 degrees, and that is all over 5.0 kilograms. And then if you plug in acceleration into your calculator, it comes out to be 1.7 meters per second squared. I just used sig figs for my answer. You could do 2 to 4. That's because the numbers represented are approximately 2 sig figs on average. And then I boxed my answer to make it really obvious to someone that I understand what my answer is. Now, because it was asking for magnitude, I do not need a direction. So that is how you solve dynamics problems. Now, we're going to go through in class and take a look at other varieties of problems on ramps and so forth. But this gives you an idea of the process and things you need to do and what your work should look like. Have a good day.